variables. And the Pearson correlation coefficient, or the coefficient of correlation. And when it comes to the regression and correlation quizzes, you're really going to have to know some definitions. And so Pearson correlation coefficient, or the coefficient of correlation, which is little r, it's going to be a difference between big R and little r in this problem, in this unit, measures the strength of the linear relationship, and that value can range from -1 to 1. So -1 is a perfect negative relationship. So negative relationship meaning that it's downward sloping, and if it's absolutely perfect, that would mean, I can't even draw it that perfect, that every one of our dots was exactly on the line. So that would be like an R of -1. Not everything has to be that perfect though. So if you look at the examples here, when it says positive correlation, positive because it's upward sloping, but those our points there are not exactly on the line. This is a strong positive relationship, so it's going to be something positive. We don't know exactly what it is, but maybe something like 0.7. It can range, right? Maybe this is R of 0. Or this would be negative, but 0.68 or something like that. When there's no correlation, that means that there's no linear relationship. It's not really going up or going down. No linear relationship. An R of 0 doesn't mean no relationship. It could also have an R of 0, but I could have a bunch of points that look like this. So if I've got variable X and variable Y, sure, there's no linear relationship. This is not a single straight line, but there is some kind of curve here. And so just keep in mind that when we're talking about correlation and the Pearson correlation coefficient, or the coefficient of correlation, we're talking about that straight line. So in order to calculate your correlation coefficient, you are going to use data analysis. So when you go into data analysis, you're going to select, it's a really tricky one there, correlation, okay? So when we go to do correlation, you can select for the input, there's basically two things. There's the input, and then it's going to output those values. And so for that input, you can select all of the data. It doesn't just have to be two variables, X and Y. But the real key here, guys, is that I know some of you don't like to use the labels when you do data analysis. You're gonna want labels. If you're running correlation for 10 different variables, you're gonna want to be able to know which one's which. And so it's gonna return the correlation for every combination of however many variables you put in there, okay? And we're gonna see this and what those charts look like. So for the first one here, it's just a simple one. There's only two variables. So use the data in the X and Y tab. What is the coefficient of correlation between X and Y? So we're looking for that R, that R between the variables of X and Y. And so we're going to run this in Excel. So when we open up our Excel, you've got lots of different data in that Excel spreadsheet, but we're just using the one X and Y, the very first tab there. And we're going to go into data. We're going to go data analysis, and we're going to use correlation. So we'll hit correlation, and we put in all of our variables as one big thing. So I've done this. All of your data that you're going to see is grouped by columns, and I've got labels in that first row, okay? So I want to make sure that I've got those new labels. And output range, I'm going to put my output in this same sheet so it doesn't open up a new tab for me, just to make my life a little bit simpler. You can do whatever you want and hit OK. And you'll see here that along the diagonal, you have ones, right? X is perfectly correlated with itself. Y is perfectly correlated with itself. We want the relationship between X and Y. So we want where X and Y intersect, and that happens in this cell here, okay? And so I love using these numbers because no matter what, they still tend to confuse us. -4.3 E -17. So if you're looking at that, and again, you're like, I don't know what that is. Remember, you can go up to general where we've got the different number types, and you can change this to a number. Right now, it's actually in scientific notation. And if we change it to a number, it's going to come out of 0. If I want to see if there are more I can increase or decrease the number of decimals. This is basically 0, okay? And it didn't ask us to do this, but if I go Control, I'll select all that data and insert a scatter plot here, we can see that when we plot this, there isn't really a relationship. We don't see like an upward trend or a downward trend. It's just kind of all over the place. And so this correlation of 0 basically means that there's no relationship. And we want to just keep in mind, technically we're talking about no linear relationship, but, as we saw in our diagram there, it doesn't really look like there's any relationship at all. So it can ask you to find the correlation between two specific variables. It can also ask you, like it does in the second question, using the data in the movie sales tab. I mean, they would just give you the file right there and you click on it. What variables have the strongest level of correlation? Which are the weakest? So it's either going to ask you for strongest or weakest. So strongest, it doesn't matter whether it's positive or negative. They're just asking for strongest. So that means we're looking for what's closest to positive or negative 1. Doesn't really matter. And for weakest, we're looking for the closest to 0. So this is from the data in the movie sales tab. So this is a situation where we have many variables going on. So we go over to our movie sales tab. We've got different things happening here. We've got first year box office in millions, total production costs in millions, total promotional, total book sales, and whether or not it was comic book based. So we're going to run this correlation. So again, we're going to make sure we go to our data. We're going to go to data analysis, correlation, and again, we're only putting in one set of data here. You have to put it in as one big chunk. We just highlight all of the data, and again, you want to make sure that you're highlighting those titles along the top there. Make sure you've got labels in first row clicked off, and I'm going to put this in my worksheet. I'm just going to choose to put it somewhere down here and hit OK. And so again, we can see that along the diagonal, we have all ones. We're always going to have all ones there because each thing is perfectly correlated with itself. We don't have numbers in the top because that would just be repeats of what we have in the bottom. The correlation between first year box office and total production costs, 0.917 there, is the same as what would go over here. Again, first year box office and total production costs. These would end up being the same numbers, so we don't care. Oops, that's not what I want to do. But we are looking for the number that has the strongest relationship. So we're just looking for the one closest to either positive 1 or negative 1. These are all positive. And we can see that the one with the highest relationship there is going to be first year box office and promotional costs. It also asks us for the weakest relationship. So we're looking for the one closest to 0. And if we do that, we're going to see over here, let's make that a different color, that is the total book sales and whether or not it is comic book based. And so if we just jot that down so that we've got it, again, that strongest situation, our strongest was our first year box office and the total promotional costs. And the weakest was the book sales and comic book. So that's correlation. Correlation is used typically in the real world when we're trying to figure out what things we might use to predict others. So if I wanted to be able to predict the first year box office sales, I'd be looking for variables that move with it, that are very closely aligned, and those are going to be things that have close correlations. We can also just run regressions. So a regression is us predicting a variable. So we're going to predict the y variable, which is also known as the dependent variable. This is another type of definition that you must know. Sometimes in the problems, they'll just refer to things as dependent, or they'll say, what is the dependent variable? You need to know that that's the y, using the independent or explanatory variables, which are your x's, by minimizing the sum of the squared residuals, okay? So a residual is just the difference between the actual y variable that you have in your data and what the model predicted, okay? You're just honestly, all you're actually doing here is finding that line of best fit, okay? And so if we just jump down here to this picture, for example, right? If I have all of these data points, here we've got the grades versus hours studied. So we've got hours studied on the bottom, which would make that the x variable, the independent variable. And then we have grade, which is the dependent variable in the situation because it's on our y-axis. And dependent means that it depends on x, that we want to explain the grade that somebody got by knowing how many hours they studied. So if we have all these data points, and these would be like real data points that we collected, we can find the line of best fit. And that line, the one that you see there, we can actually get Excel to give us the equation for that line. And it's figuring out what line would be that best fit by taking the difference between the point that we actually have, the dot, and what our model would predict. Because that point on the line, if I know that I studied 10 hours and I plug in x equal to 10 into the model, that is going to give me the predicted y values, what the model predicts, and that's the point actually on the line. But the actual data point that we observed in real life, that's the y. And we're trying to minimize the difference there, and that difference is the residual, okay? And that's another little r, different little r. This little r, the residual, is a different little r than your correlation coefficient, okay? But we just want to understand that we're trying to find the line that is as close to all the points as possible, okay? And so these x variables, these independent variables, are theoretically things that we can control. And these x variables they can be continuous, so they can be a number, or they can be binary. They can be 0 or 1. They can basically be answers to yes or no questions, and we'll see that in one of our examples. When we run a linear regression, so this situation here, grades versus hours studied, this would be a simple linear regression. We see the simple linear regression, we try to predict y by using beta naught, which is the intercept, and then beta 1, which is our coefficient. And the betas are what Excel gives us. And so here, when we see this equation, y equals 63.12 plus 1.7527x, this is telling us that the intercept, beta naught, is 63%. On whatever this is, there's an idea that even if you studied 0 hours, that even if x was 0, that the y value you would get would be 63.12. You could get a 63% on this test even if you studied nothing at all. We were wishing that quiz 4 was this situation here. And so then what we see for beta 1, that coefficient, is 1.75. This is basically telling us that 1.75, that our grade, right, if x is the number of hours studied, and y is the grade, that 1.75 is telling us that y will go up, that your grade increases by 1.75 for every extra hour you study. We can have a multivariable regression, which just means that we have more than one variable going into the problem. So like instead of it just being grade, us predicting grade based off hours studied, maybe it's the grade on the quiz as a function of hours studied and what grade you got on the last quiz and how well you did in high school math and how many hours you slept the night before. Like multiple things could be used to predict this, okay? So again, we have to keep in mind the idea of dependent versus independent. So here it says, example 1, predict the price of a house using square footage, number of bedrooms, and if there is a garage or not. What is the dependent variable and what are the independent variables? So we need to recognize dependent variables are y, and it's the one you're trying to explain. The independent variables are the x's, and you're using them to do that explanation. So if we're trying to predict the price of a house, that means that the dependent variable is house price. The y would be our house price. And for our independent variables, that's going to be anything that goes into that. And it tells us to predict it using square footage, number of bedrooms, and whether there's a garage or not. So our x's are going to be square footage, number of bedrooms, and whether or not we have a garage. So that model, we don't know what the intercept is, but we would just say beta 0. We don't know what the coefficient is going to be, but we're going to figure out the relationship between square footage and house price. Beta 2 times that number of bedrooms. And our beta 3 times whether or not we have a garage. And something like number of bedrooms, hopefully that's pretty explanatory. Like if it was a 2-bedroom house, you put in a 2 for x. If it was a 5-bedroom house, you put in a 5. But for that x garage, this is answering the question of whether or not you have a garage. So it's going to equal 0 if there's no garage. And it's going to equal 1 if they have a garage. It's this idea of a yes or no question where we want the 1 to go with the yes. A little bit like those binomial variables we worked with early on. They're like either happen or don't happen, but this isn't something left up to chance. It's just us recording the data. When we're like, hey, how do I put this into an actual mathematical model? I'm going to record it as a 1 or a 0, okay? And so if we look at question 2, it says, if the resulting model was, so they, and by they I mean I, have made up this theoretical magical model here, okay? Let's say Excel gave us this answer. So the intercept is 50,000, right? That's our beta 0. Beta 1, 100. Beta 2, 5,000. Beta 3, 15,000. So it asks us, what's the predicted price of a house if the home had 2,000 square feet, 3 bedrooms, and no garage? So to get that sales price Y, we're just going to plug in the values there. So 50,000 is our intercept plus 100 times, what's our square footage? Well, it says 2,000 plus 5,000, the number of bedrooms is 3, plus 15,000, but it says I have no garage, so for that last x term, right, this x term here is a 0 or a 1. It's answering a yes or no question, and it says there's no garage, so we're going to put in a 0 there. And then we calculate that out. I don't know why that appeared so silly, so sorry. So we take our 50,000 plus our 100, times our 200 there, and again, that 200, or sorry, 2,000 is the number of square feet, plus the 5,000 times the 3 bedrooms, plus the 15,000 times 0, and we're going to get $265,000 for this house. Now, clearly there's more factors that are going to go into the price of a house, like where it's located, windows, furnishings, all kinds of things, but you get the idea here. So it asks us for part B, what's the impact to sale price if the home had a garage? And so this is just asking us about that beta 3, which is 15,000, right? If that X garage equals 1, this means that when we calculate out that price, no matter what we had in the beginning of the equation, instead of adding the 0, right, because 15,000 times 0 is just 0, like it went away, we're going to add the actual 15,000. Anytime you have these yes-no variables, the impact of them is whatever the coefficient is. It's basically showing us that there's two different lines. There's one where there's no garage, and there's one with a garage. And this garage line is 15,000 higher than the no garage. So if we were at the intercept of our equation up above was 50,000 bucks. Not that you would have a 0 square foot home with no bedrooms, but theoretically, like it's just a lot kind of thing, I guess. It's just $50,000. If everything else you're plugging into the equation was 0, it would just be that intercept of 50,000. But if it was 50,000 plus you had a garage, it's going to be that extra 15K. So that you're going up by that 15,000 bucks. So the entirety, no matter what you have for square footage and number of bedrooms, it's going to go up by that 15,000, that intercept of that yes/no variable, whenever you have a garage. So that impact is just going to be 15,000. Whatever your sales price is, the impact is going to be an extra 15,000 if you have a garage there. So when you run a regression, which we haven't done yet, I've just given you a regression model, there are 4 assumptions. These assumptions you must, again, memorize. I don't know what it is about this year, but people kind of think that they should they read it once weeks ago, and so they should have it on their quiz. When I talk about like we need to memorize and know things like know our steps for hypothesis testing question, know our steps for type 2 error, know the definition of the Pearson correlation coefficient, these are things that you have to memorize. And if you don't have them, if they're not ingrained from just doing a bunch of practice, you need to write them out a bunch of times until you've got them, okay? So these are 4 things. You need to have these assumptions. I know in class they go through and they actually dive into these very deeply, but for the sake of the questions here, we really need to just make sure that we know that these 4 rules exist. There's going to be a slight convolution with one of them, but so because I'll ask you like which of the 4 is or which of the options is not a rule, or which of them is a rule, and they kind of list out 5 options and you need to know the 4 rules. So the residuals, and remember, residuals are just the error terms, right? They are whatever your actual y value is minus whatever your model predicted. And anything with a hat in regression means that you predicted it. So they must have a mean of 0. They must have a constant variance. So constant variance means that if you were to scatter plot them, the scatter plot looks about the same, okay? Like it's got the same width all along. Residuals must be normally distributed. So this means that if you built a histogram of these residuals, and the histogram goes back to quiz 1, but you might have to build a histogram, that histogram looks like a normal curve there, okay? It's got that bell-shapedness, and it should also, be centered at 0, right? If our average is 0, from rule number 1, your histogram should be centered at 0. And rule 4, the residuals must be independent. So again, if you made a scatter plot of all these residuals, if they had like an upward slope, that is not independent. But if they were just a total scatter plot, they would be independent. The only thing you might have to do is actually build your histogram of residuals, okay? So regression results. How do we actually do this? So this is what regression results are going to look like in Excel. I've kind of filled in what everything is here, okay? It's going to look like a lot right now, but you're going to, after you run a few regressions, you'll just grab exactly what you need. It won't be too hard, I promise, okay? So if you want to run a regression, you're going to go into data analysis and you're going to choose regression. For your y variable, keep in mind that is your dependent variable. It's what you want to explain. And so you would highlight all of your y variables. Your x variables are your independent variables. And you might have more than one independent variable, but it's the ones you're using to explain, and the key here is that they must be beside each other. You have to put in, if you're trying to run a regression with 3 different x variables, like we had up here, square footage, bedrooms, and whether or not there's a garage. And in between bedrooms and garage, there was a column of data like how many windows the house has. You'd have to delete that column of data so that it was square footage, bedrooms, and garage all smacked right against each other so you could put it in as one thing. Okay? And so when you run a regression, this is what you get back. Okay? There's kind of 3 components to this. There's the regression statistics at the kind of little top chart there. There is the ANOVA, and then there is what we typically call the coefficient table, okay? And so that coefficient table is where those betas are gonna come from. So something like the 100, 5,000, and 15,000 from this model up top, if we ran a regression, these would be the numbers that were actually like it would say intercept, and there would be 50,000 in that spot. It would say not waste, this is a different example, but it would say square footage, and then there'd be 100 there. It would tell us what the value of those coefficients are, okay? Everything on here is of use. All I want to point out is where some stuff is right now. We're going to come back to what everything is in the end. So our coefficients here are super key. That's the actual model that we're going to be using, okay? There's going to be a p-value that goes with each of those coefficients. We are going to use those p-values. This is where it's going to come back to using some of our knowledge from our third quiz, where turns out we're running hypothesis tests, but it's okay because they're the standard same thing every single time, okay? Our r squared and adjusted r squared are going to be numbers that we use. Next to them on this page are some calculations for them. They're also on the next page, but don't worry about that right now. And just some really interesting things. So the observations there, this one happened to be 250. Our number of observations is n. And if it's multiple regression, meaning multiple x values, k is the number of slope terms. Basically, it is the number of x's in our regression. And so when we look at our ANOVA table, when it says the degrees of freedom for the regression, that is k. That is, again, the number of x variables. The degrees of freedom total is n minus 1. So whatever the observations were, minus 1. And the degrees of freedom for the residual, or this is also sometimes just called, again, the error, is n minus k minus 1. And so sometimes we can use partial information, if they kind of give us like a part of an ANOVA table, to back out how many x variables were in the regression or how many pieces of data we had in our regression, things like that, okay? The last thing that's going to be of importance to us on this, so again, we've got our coefficients down below, so the actual values of the regression. We have the p-value that's going to go with each of those coefficients. We have the r squared and adjusted r squared, which we're going to come to later, but we just want to know where to find them in the output. And then under significance F, there is another p-value, because there's actually 2 different types of hypothesis tests going on. The one down here is a t-test, and the one over here is an f-test. Different f-test, different t-test than you did on your last quiz. So when it comes to assessing the model, it's not just enough for the Excel model to spit out, hey, Sale price is 50,000 plus 100 times whatever square footage plus 5,000 times bedrooms plus 15,000 times whether or not we have a garage. We need to actually know whether the model we're making is good or not, okay? So again, this coefficient column is going to give you the model. Everything else, these other three things that we've highlighted here, the other three clumps, they are going to be how we figure out whether our model is good or not, okay? So assessing the model. There are three ways to assess the model. So this is our big idea right now. We want to understand that there are three different ways. There's an F-test for the overall model. This is going to tell us, does the model have any value? The T-test for individual coefficients. This is going to be basically answer the question of, does X explain Y? And what that really comes down to in a practical sense is, should X be in the model? And then we're going to look at the R squared and adjusted R squared values, and they're going to tell us how much of Y as a percentage is explained in the model. So these are going to be very standard. They're going to be the same for each problem, okay? And as I have it listed here, I've listed the null and the alternative hypothesis, and I've written them out formally, and then I've also written next to them that practical interpretation. And thankfully, they are the same for every single regression that we run. So for the null hypothesis for our F-test, the null is that all of our coefficients are 0. And so what that is implying is that whatever that intercept would be, we don't really care about that intercept, that it's 0 times x1 plus 0 times x2 plus 0 times x3. And if all of our coefficients are 0, then that means the model has no statistical significance. It does not help explain why. Nothing is explaining why. No matter what you put in for x's, if the coefficients are all 0, y is going to be 50 every single time. That basically means the model is shit. Very practical statistical analysis there. You've got a crap model, okay? The alternative is that at least one of those coefficients is good, okay? That at least one of them is okay. And the takeaway here is that we want to reject the null. We would like our null to be wrong. We want to reject it, which means rejecting the null is a good thing in this case. So the rules of our hypothesis testing still apply. If that p-value is smaller than alpha, we're going to reject the null. It's just that in this situation, that's a good thing and we're happy. It means, again, as it says here, the model has some value. If that p-value from the F-test is smaller than alpha, we don't reject the null. And not rejecting the null, that is a bad thing. It means our model has no statistical significance. How do we get that p-value? Well, thankfully, you don't have to do any calculations. Yay! Excel's going to do that lifting for you. It's in the ANOVA table. And so that is where, when we're looking at that regression output, under ANOVA, the second kind of chunk there, under that significance F, that is the p-value for the F-test. Excel is going to give it to you. You are never going to calculate it on your own in this course. So that's for the overall model. The one we're going to use most is actually for the individual coefficients. It's basically the exact same idea as the F-test, but instead of the null being that everything is 0, it's just for the specific coefficient that we're looking at, okay? I have it written down here as BI, so that little I is like a stand-in for whatever coefficient we happen to be looking at, but we're gonna look at a specific one. So that null is that, that coefficient is 0. And if it's 0, practically speaking, that means that it does not explain why. And the other way of thinking about this is that it should be removed from the model, okay? This page here is the page that's going to save you in the first week of COM 172 next year, where you start running regressions on the very first day of class, okay? The alternative hypothesis, which is good, the null, which is bad, is that it's not 0. So this is the difference between our model being, hey, y is equal to 50 plus 0x1 versus 50 plus 10x1. If the coefficient, and by coefficient we just mean the number in front of the x, is an actual number, and that's what the alternative is saying. Alternative is saying is that BI is a number, it's not 0. Then when you change the value of x, it's going to change the value of y, and that means there's a relationship between x and y. If, in that null hypothesis, that coefficient is 0, again, that's a bad thing, then when you change the values of x, you're still going to get 50 for the value of y, so there's no relationship between x and y, okay? The same rules apply for all of our hypothesis questions across the course. If our p-value is smaller than alpha, we reject. Somebody comes with a tiny piece of pizza, we're like, reject you. But it just turns out that rejection under regression is a good thing. It means, again, that x variable helps explain y and should be included. And the p-value being bigger than alpha means that we don't reject the null, right? Somebody gives you a giant piece of pizza, you're not going to reject them, you're like, thank you. But turns out for regression, that's a bad thing, okay? For our t-tests, our p-values for these are located in the coefficient chart of our regression output under the p-level, and there's a p-value for every coefficient. So in that coefficient, these are the p-values, okay? And you're going to have a p-value for every coefficient that is in the model, because you want to check if each of them are going to be statistically significant or not. Are they good to have or are they not good to have, okay? And so for our last thing here, so the f-test and the t-test are really about whether or not whether your model's worthwhile or not. Like, is this good or bad? It's like a yes or no question, right? We either reject or we don't reject. And in this, for regression, rejection's good. It means that our model is good. But the r-squared and adjusted r-squared tell us how good the model is, okay? And the goal here is we want our r-squared, big R-squared, to be as close to 100% as possible. 100% would mean that we have a perfect model. That never happens with real data. Anything, usually anything like of 70% or more we're pretty happy with, but that's going to be dependent on the situation that you're in. But we want our r-squared to be as big as possible. So r-squared, big R-squared, called the coefficient of determination, not to be confused with the coefficient of correlation, which we did in the first page, tells us the percent variation in y, which is your dependent variable, explained by your independent variables. Whatever the percentage is, it tells us how much of what's going on with y, all the ups and downs, is actually explained by the x's. As your number of independent variables increases, this is an important fact for some true-false questions, r-squared tends to increase, and so we use the adjusted r-squared. So r-squared and adjusted r-squared are actually kind of the same thing. It's just that r-squared accounts for the number of variables that we have. Right? And the number of variables, as we kind of mentioned before, is going to be k. So that adjusted R squared is the same interpretation as R squared, but it, literally, as I said, it has been adjusted to account for the number of independent variables, K. So there are lots of different ways to calculate R squared. For the most part, Excel is going to spit it out at you. So this model here, the R squared is 0.72%. The adjusted R squared is almost the same, unless you go to that third decimal there, right? R squared would be 0.727, adjusted R squared 0.722, okay, or 23 if you round there. Sometimes though, we're not pulling the R squared from the regression we're running. We have to calculate it from whatever partial information they provide to us in the problem. So there's a couple different ways to do this. First off, we can take little r and square it. So this is your correlation. So if little r was 0.6, let's say, then r squared is going to be that 0.6 squared. And so our r squared there of 0.36. Note that even if this was negative 0.6, r squared is still going to be 0.36. So you can go from little r to big R squared, but you can't go backwards, right? Because if I try to take the square root of 0.36, I get plus or minus. I get two options, so I don't actually know what R would be. So you can find, if you know the correlation, you can find R squared, but if you have R squared, you can't find correlation. The actual calculation for correlation is the sum of squared regression over the sum of squares total. This is what this SSR and SST means. And so for our SSR and our SST, these come off of, these come off of our ANOVA table. That sum of squared regression is going to be in the first SS spot under SS, but where it says regression. The sum of squared error, if we need it, EE, is going to be in the second spot, and the sum of squared total is going to be in that total spot there. And we're going to see that in a moment when we start running some problems. Now, if we need to find our adjusted R squared is another thing that they like to give us, that we can get just from our regression. But if we are doing this again from our partial type of calculations, sometimes we have to calculate it ourselves. Typically speaking, so we see this first big kind of question, big calculation here. This is typically not necessary. The second one is typically what we are using. In the type of problems you guys have, they tend to give us R squared, and then we calculate the adjusted R squared from there, okay? And so it's 1 minus R squared, that's in brackets, times 1 minus n, that's just our degrees of freedom total, right? If we go back to our ANOVA table there, you'll see that degrees of freedom, right, for regression it was k, for residual it was n minus k minus 1, and for our total n minus 1 there. And so our degrees of freedom n minus 1, that's just the degrees of freedom total, and the n minus k minus 1, that's just our degrees of freedom of the error term, okay? So sometimes we have to flip between the two, okay? So let's actually run some of these regressions and go from there. It says using the data in the verbal and math tab, run the regression of y equals beta naught plus beta 1 x1, where the independent variable is math and the dependent variable is verbal, okay? So we want to, it says dependent variable is verbal, so that means verbal is going to be our y. And we want to get the model, okay, where we're going to be explaining verbal with math, and it asks us What's the resulting model? So basically that's just asking us for the equation, and is it significant? We're going to look at that F-test and T-test there. So when we look at our regression model here, so we verbal and math, again, to run that regression, we're going to go to data analysis. We're going to go to regression, okay? And so just above where you've got those t-tests, you've already used regression. And it asks you to input the y range. So that y range is going to be whatever variable you're trying to predict. So that was verbal. The x range, in this case, we only have one. It's going to be our math scores there. And there's a lot of them. So I really suggest that command shift down. Otherwise, you're going to be scrolling 500 rows. Labels, we hit yes. You're never going to use this constant as 0 thing, so don't worry about that. Confidence level, it's already going to spit out confidence intervals to you, so you don't really have to worry about that either. But something I would suggest that you always click off is just click for the standardized residuals, okay? And we'll just click on these for a second so I can show you what they are, but standardized residuals, I always want you to click, okay? And so now I have my regression output that looks a lot like, a little bit simpler than the one we had before, but a lot like what we had in our example there. So we've got our R squared and our adjusted R squared. We have our ANOVA table where it tells us our degrees of freedom for the regression, the residual, the total. We have the sum of squared issues here, mean squared, and then the F calculation. And we're going to talk about these later because one of the questions they love to do is kind of give you partial information from the ANOVA table and ask you to calculate things out, okay? And it turns out, you know, for sum of squared total, that number there, that 4178193, it is literally just the sum of the two numbers above it, okay? You get the same number there. If I wanted to calculate this MS for regression, the mean of the squared regression, it is whatever number you had in the SS divided by your degrees of freedom, which in this case gives you the exact same number as you see. For the MS for the residual, it's the SS from residual divided by what comes before it. So again, you see that number there. And then if you want to get this F term, it's the ratio of the two terms that came before it. So it's that mean squared from the regression divided by the mean squared error, or mean squared residual, and you will get that F term. And that is where, that F term is where this p-value for the F test comes from. But before we get to that, we have our equations here, okay? We have our intercept is 176 and our coefficient 0.56 there. If you scroll down, you'll see I've got residuals, and all it really did is it took the predicted verbal. So this is what our actual like our model predicted, and it calculated the residual, and then it turned it into a standard residual. These are just Z values, okay? It turned all those residuals into a Z value there. So when the question asks us what the model is, we found out that it's Y, right? Our verbal skill, or score, sorry, that the intercept was 176, and the coefficient was 0.56 times whatever our math score was. And it asks us if the model is significant. And so for the model to be significant, remember, we like small p-values, right? That is a good thing for regression. So if you go back to the model, you'll see for significance F, anytime you've got this e to the negative number, like 43, that is basically 0, okay? This number is basically 0 there. And so for the F test, if we were to do that F test and look at whether or not there's any significance, that has a p-value of basically 0. Again, we like small p-values. right? That's a good thing. It means that we reject the null, that there's no value in the model. And we could look at the t-test for the coefficient of math. So the p-value for that, because we only have one variable in it, it really doesn't matter whether we look at the f-test or the t-test. The f-test is just like doing all the t-tests at once almost. And so if we look at the p-value here, the p-value for math, again, basically 0. And because we only have one variable, these are actually the same numbers, okay? We have the same number for the f-test and that t-test. And so that t-test, again, that p-value is basically 0. And for that t-test, remember that the null is that the coefficient for math would be 0. And again, that's a bad thing. Against the alternative, that it is any number other than 0. We don't know what number it is. I mean, the model predicted 0.56, but we're just saying, yo, it's not 0, and that's a good thing. And with a p-value of 0, which is going to be smaller than alpha, and for these questions, they're rarely going to tell you what alpha is. Alpha is just always going to be 5%, okay? So that p-value less than alpha, we are going to reject the null. And when we reject the null here, that is telling us that beta math is a number, and therefore the variable for math helps explain why and is good in our model. So it asks us, well, what is the coefficient of determination, which is r squared for this model? So if we go back to that Excel sheet, that r squared, 0.34 there. And so that value, our r squared, our 0.304, this is telling us that about 30.4% of verbal scores, actually not of verbal scores, but of the variation in verbal scores, so the amount the verbal scores are going up and down is explained by math scores. That's actually, so this is not a very good one. We can only explain about 30% of what's happening. There is some relationship. We saw that because of the t-test, right? We said that that coefficient is a number, that it belongs in the model. It's just that it isn't everything. It doesn't explain everything what's going on in the verbal scores. It's only explaining about 30%, okay? So question 2 here says, using the annual sales tab, use all available information. So now we're going to run a multiple regression to predict annual sales. It asks us what variables should be included in the model and which should be removed. So anytime we're talking about what should be included or removed, we're talking about that t-test, which again had the null, that whichever one we're on, that the coefficient is 0 versus the alternative, that coefficient is not 0. And if it's not 0, it means that we should keep it in the model, right? It means that the x helps explain y. But if the coefficient between the x and the y is 0, this means that we should probably remove it, that x does not explain y. So we're going to run it, we're going to run this model, and we're really, when all it's really asking is what variables should be included and what should be removed, we're going to look at that p-value on the regression, or on that regression result. So when we look at the Excel and we want to go to the annual sales tab, okay, it asks us when we run our regression, so we're going to go down analysis, go regression, hit OK, that our y variable, the one we're trying to predict, is annual sales. And that for the x variable, it asks us to use all available information. So we've got square footage, inventory, ad budget, district, number of competing stores, And we're going to select all of that. Okay. And we're just going to hit OK there. It's probably going to freak out at me a little bit. My computer just running way too many things. There we go. Okay. Turns out I need to hit the X and not OK. So we get this model here. And, oh, I didn't go over those residual plots. I'll talk about that in just one second. Okay. So in this model, oh, we can see that for this R squared, we have 99%. This is a great model. Our adjusted R squared is a little bit smaller, but also is a great model, right? You use either one there. And the main thing here, guys, if we wanted to actually build the equation, that's where these coefficients come into play, okay? This would be telling us that the y of our sales there is equal to, well, our intercept is negative 35.58 plus 20.41 times the amount of square footage, minus 0.007 our inventory plus 16.9 whatever our ad budget is, and it would keep going. But what this question was really asking us is to analyze the p-values, because for each of these, it's going to be about whether or not we want to keep it in the model, okay? And so what we see, remember that we like small p-values. So if the p-value is smaller than 5%, we're going to keep it. That means it's a good thing. So when we're looking at these, the intercept is more than 5%, but we can never remove the intercept. We don't control the intercept. We control the variables, okay? For square footage, that's a small number, so we're going to keep it. For the inventory, that's a big number, so we want inventory out. For our advertising budget, that's a small number, so it's okay. The size of the sales district, that's a small number, and it's okay. And number of competing stores, 0.0545. This is just above 5. So technically speaking, we're going to remove that number of independent or number of competing stores. But in real life, we'd probably remove inventory because that one is really bad, 86%. That we definitely want to kick it out. And then see if when we reran it, if number of competing stores became significant, if it dropped below that 5%. So when it asks us which of the models should be removed, we want to remove any variables with the p-value greater than 5%. And so in this case, that is the inventory variable and the number of competing stores. And so we would keep the rest, and we would keep the intercept even though the intercept failed that test. My favorite type of question. There's a lot of these ones. They seem really hard, but it's more about just memorizing, not even the formulas, but kind of the flow of this chart, okay? So it says the following is an ANOVA table for regression. So let's just reacquaint ourselves with that ANOVA table from our regression, okay? Right, we have that degrees of freedom for the regression K. K was that number of X variables that we had. The residual, N minus K minus 1 degrees of freedom there. And the degrees of freedom total is N minus 1, where N is that number of observations, the number of basically rows of data in our set there. The sum of squared regression, sum of squared errors, and sum of squared total, you'll never calculate yourself, but you might have to get one of them, because what really we have there is that if you add the sum of squared regression to that sum of squared error, it's going to equal that sum of squared total. The MSR, that mean squared regression, is, and so again, these are formulas that you can memorize, or you can kind of memorize that it's to get what's in this third spot, we're taking what's in the spot before and dividing by the degrees of freedom that came above it or before it. And that F is the ratio of the two numbers before it, the MSR over MSE, okay? And again, these are formulas we can memorize, or we can kind of memorize this flow of the chart. I, in all honesty, for the most part, like to just kind of fill in the chart before I even calculate or go from there. So for our sum of squared total, right, it's just going to be that 9,000 plus the 300, okay? For that mean squared is going to be 9,000 divided by 4. You're just taking what came before it there, and going from there. And again, you can memorize the formula that it's the SSR, divided by K, or kind of understand that graphic there and be like, okay, this is going to be 2,250. Again, for the MSE, we can take our SSE and divide by n minus k minus 1, but really all that is the 300 divided by 5 there, and so that's going to be 60. Our F term is our MSR divided by MSE, but again, it's the two terms that came before it. We're going to divide there. We're going to take that 2250 and divide by 60, and we're going to get a value there of 37.5 for that F value. So for the actual questions here, how many independent variables were in this regression? K is the number of independent, I cannot write here. K is our number of independent variables. And K is, in that first spot, degrees of freedom regression, so it is 4. We don't know, we didn't see this data, we don't know what's going on, but we do know that it is 4, okay? Was the regression significant overall? This is going to be us looking at that F test, and that number under significance F, this is the p-value for the F test. So our p-value here, 0.0062, is a smaller number than 0.05, right, our alpha. And remember, small p-values are good in regression. So in this case, it's a small p-value, so we would say, yes, it is significant. Our sum of squares total, our SST is just our SSR plus SSE. You can memorize that formula, but then you also have to memorize what each of those things are. I just like to kind of nib the chart. Like, hey, that bottom row is equal to the first two added together. So that's that 9,300. It says, what is the F statistic which was used to find the p-value of the F test? So that F statistic is just that F value of 37.5 that we found. And again, that is the MSR over MSE. Actually, I can't believe I didn't ask this, but what is the R squared term? R squared, our coefficient of determination. Sometimes it asks for it by name, the determination. That coefficient of determination, oh, I don't want that line, I don't want you to think that's division, that R squared is equal to the SSR divided by SST. It's whatever that sum of squared from the regression is over the total, And this is going to be a good model. I didn't actually calculate this out, so just 1 second. This is going to be a great model. This is 0.968 there. That is a lovely model. If we wanted the adjusted R squared, well, remember that the adjusted R squared, we would just use the formula of 1 minus R squared, and then that n minus 1 over n minus k minus 1. And so for us, 1 minus 0.968, n minus 1, right? N minus 1 is just your total degrees of freedom. So that is 9, and n minus k minus 1, it's your degrees of freedom from the air. And so we've multiplied that out. Let's take a look at this question here. This is an actual question from your practice problems. These are just ones that people send me a lot of. So Abby Kratz is a market specialist in the market research firm of Saz, Sykes, and Spiz. What are these names? They're analyzing household budget data collected by her firm. Abby's dependent variable, dependent variable, that means it is your Y, is monthly household expenditures in dollars, and her independent variable is annual household income in thousands. Careful on those units. Regression analysis gives us this. So their regression output doesn't look like your regression output. If they make you run a regression yourself, it's going to look a little bit different than this. But all the information is here. You've got that coefficient value. It's telling you that your coefficient there for the intercept is 39.14, that the coefficient for x, so this is your beta 0, and this is your beta 1, 1.79. And it gives you the ANOVA table. Okay. And so it doesn't actually give you the p-value for the f-test, but it does give you the p-values that go with the coefficients there. It gives you your r squared, and that can be important. So it says, using an alpha of 5%, Abby should. And then we get reject H naught of beta 1, not reject, suspend judgment, increase the sample size. Trick. Suspend judgment and increase the sample size are always options, but they are never the correct answer here, okay? So we basically want to recognize whether we're going to reject or not reject for each of our t tests. When you've got this H naught beta 1, H naught beta 0, these are referring, right? These are results from those t tests. And that's where we're going to look at the p-values, right? Remember, if the p-value is smaller than alpha, we do not reject the null. And another way of saying null is saying H0. If the p-value is bigger than alpha, then wait, did I just write that backwards? I did. If our p-value is greater than alpha, we do not reject our null. If our p-value is less than alpha, we reject the null. But remember, rejecting the null is a good thing in regression. So for our intercept, the p-value, this is bigger than 5%, which means that we are going to, do not reject. And since this is the do not reject for the intercept, this is do not reject that H naught of beta 0 equals 0, right? That's the null hypothesis if we're talking about the intercept, because the intercept is beta 0. For the second one, this is less than 5%, and so this is going to be a reject, and that's a good thing, but it's reject that null that beta 1 equals 0. So when we look at the options, you've got to really get yourself sorted out like I just did here before you look at those options. It will screw you up. You basically want to true false each of them. Reject that H naught for beta 1 is 0. Do I want to reject the null for the intercept? Yep, that's exactly what I wrote above. Not reject. Well, we just said we were going to reject for beta 1, so that's not correct. Reject for the intercept, right? Beta 0 is for our intercept. Nope, we said above do not reject, so our answer there is going to be A. Okay, we're going to do this again. Louis Katz, an accountant, again, more weird names, are analyzing manufacturing costs of molded plastic telephone handset. Okay, Lewis's independent variable is production lot size. So this is our X in thousands of units. His dependent variable, so his Y, is the total cost in hundreds. And we have our regression results below. Using a 5%, Lewis should, and again, we've got this increased sample size and suspend judgment. Psh, no, never the option. We got this reject, do not reject crap. Don't even look at the options. Just don't even look at them. Just, you have to remember without hesitation, right? That if you have that p-value and it is smaller than alpha, small p-value, you're going to reject the null. And if the p-value is bigger than alpha, you do not reject. So if we look at our p-values here, these are both smaller than 5%, right? 0.05. So you're going to, in both cases, reject the null. If we're talking about the one for the intercept, then we're going to reject that H0 for beta 0 equals 0. And we're also going to reject the null, but that is also for beta 1, right? Because that first one is going to be beta 1. So we have a do not reject, do not reject, reject, beta 1 equals 0. So you kind of just do the analysis and then look at the options there. Okay, I didn't actually use the one that from the questions, but this is a classic question where people are like, oh my God, I know nothing, I can't do it, my life is awful. And then when you go back and reread the question, you figure out how to do it, okay? This says, if Lewis produces batches of 10,000 units, then what is the total cost of the lot? So we want to recognize that X was the batch size, Y was the cost of the lot, and from the model gave us the equation that Y is equal to 3.996 plus 0.358. But here's the thing, guys. It tells us that it produces it in thousands of units, that the lot size, that batch size, is in thousands, and that the cost is in hundreds. I don't know why you do anything in hundreds. That seems ridiculous. Thousands, I can understand. It's like instead of saying 10,000, you're going to say 10K. The hundreds is literally just to mess you up and see if you understand how units work or not, okay? And so, oops, I forgot the X on this equation. And so when it tells us that we're producing in batches of 10,000, that's telling us that the X variable is equal to 10. Because this is in thousands, 10 is really 10,000. So when you go to plug into the equation, you have to plug in just 10. And so the thing about this question is really about these units, okay? And making sure that we're plugging in and converting our units correctly there. And it's not just about the X going in, because so for this Y, we're going to calculate this Y out, and it's 7.576. But remember that this is in hundreds, okay? And typically the multiple choice answers, it's going to actually want the answer in dollars. And so if we want this in dollars, right, if we had 10 and it's in thousand, we could multiply 10 by 1,000 to get to the actual number, right? If I take that 10 and I multiply it by 1,000, I get back to the number of 10,000. That one makes a little bit more sense. Because hundreds, we don't work with that in everyday life. But if I take this 7.576 and then I multiply it by 100, and it's just moving the decimal there, but what we get is that this is $757.60, Okay, that is a question that comes up quite a bit, but is often a struggle. Okay, and it's just a struggle because we read things too quickly. We don't read every word of problems typically. Even when I was reading through it, I was like, what are we making? Headsets. I don't really care. Handsets. Okay. I do it too. But remember to watch for units in these problems because that can really mess us up. Okay. Good luck, guys.